Hello, ladies, gentlemen, and in between, and welcome back to another episode of Maths with Hamblin with your beautiful host, Hamblin. And today, my boys, we're going to be deriving and using the distance formula. Let's have some fun. Okay, so to start, we're going to consider the case where the 2 points are both in the positive quadrant of the xy plane. So where all the x values are positive and all the y values are positive. And that's because that will make this first part easier. And don't worry, we're going to prove that the formula we derive for this case also works for anywhere the points may be in the xy plane, negative coordinates or not. So our main goal is to find an expression involving the distance between 2 points on the xy plane with coordinates x1, y1, and x2, y2. Now, this is the clever part, right? We're going to use Pythagoras to do this. We're going to draw this right triangle here, connecting the points, and then if we can find an expression just for this side and for this side, we can square them, add them, and set them equal to the distance squared, and then we'll get our distance formula. Okay, so how are we going to do that? Well, we're going to do a very similar trick as we did in deriving the equation of a circle video. If you haven't seen it, I highly recommend. Right? So we're going to draw out the x-coordinate of the first point, or the second point in our case, but it doesn't really matter. We're going to draw out the x-coordinate there as a literal length here to here, and that length is given by x2. And then we're also going to draw out the x-coordinate of the other point, x1, which is this little length here. And what I hope you can see here is that this little leg of the triangle here is equal to the big length, x2, and then take away this little length, and then you're left with the length of this leg of the triangle. And similarly, we can do it here. Draw out the y-coordinate, and then draw out the other y-coordinate, and then we can get that the other leg of the triangle is y2 minus y1, and then we can say x2 minus x1 squared plus y2 minus y1 squared must equal the distance squared. And then, of course, final step, we take the square root on both sides and we arrive at the formula that the distance between any 2 points on the xy plane, or at least in our case, in the positive quadrant, is the difference between their x-coordinates squared plus the difference between their y-coordinates squared and then square rooted. It's very Pythagoras-y, very big Pythagoras vibes from this one. Anyway, so let's get on to the case where these coordinates of these points can be anywhere in the xy plane. So we're going to show why this formula still works, even if we have negative coordinates and all that jazz. Anyway, let's get on to that. Okay, so now let's show why that the distance formula we just derived in the last section still works when you've got negative x coordinates and possibly negative y coordinates. But we're just going to show it for the case where there is negative x coordinates, because the exact same line of reasoning would still work if you had negative y coordinates, just perpendicular. Anyway, so let's say you're trying to find the leg of this triangle, i.e. you're trying to find the x2 minus x1 squared in your distance formula, and you're trying to apply the distance formula, and you take negative 10, subtract negative 6. I mean, how is that going to work, right? That will give you a negative length. Surely that can't work. But, watch this, right? So let's do the same thing where you draw out the y coordinates. Negative 10, negative 6, and now let's apply the distance formula. So let's do negative 10 minus 6. So if we do negative 10 minus 6, these two minuses become a positive, and then we get that negative 10 plus 6, which is the same thing as negative 4, which is this exact length here, or at least the negative version of that length. The length of this triangle leg is 4, but it's actually the negative version. And the reason why that is by doing negative 10 minus 6, it's the same thing as adding 6 to minus 10. Or in other words, you take away this much by adding 6 to 10, because remember, when you add to a negative number, you move it up, you kind of make it less negative, if you know what I mean. So you're going to take away this bit and you're left with this, the negative version of that length. And when you square that, if you square negative 4, that's the exact same thing as squaring positive 4. So putting it into the distance formula, it won't make a single difference, because the distance formula only cares about the square. So even if you have negative x coordinates, it still works. And here's a bonus thing. It doesn't even matter what order you put the x coordinates in. Say you did minus 6 minus 10, because to find the difference between the x coordinates. If you do some maths in your head, that will give you positive 4, which when you square it, it's the same thing as negative 4 squared. So in fact, what we've also found is because the distance formula relies on squaring the differences between the coordinates, it doesn't actually matter the order of which you use your coordinates and which ones you subtract them in, which is pretty epic if you ask me. Anyway, This completes our full derivation of the distance formula, and now we're going to apply it to some problems. Okay, so this first problem goes like this. The points -6, 1 and 2, -2 form a straight line. If that straight line happens to be the diameter of circle C at center -2, -1/2, what is C's equation? Okay, so we've got to figure out the equation of a circle, which means we've got to know the circle's center and we've got to know the circle's radius. Well, we already know the center, so bingo. And I'm sure you've already figured this out. It's quite easy. To get the circle's radius, we're going to need to, well, we've got 2 points that form a diameter. And using the distance formula, we can figure out the distance between those 2 points, i.e. the diameter of the circle, and then we can half that value to get the radius. So let's do that real quick. So let's open our square root. And now we need to find the difference between the x-coordinates of the points, which, and remember from the last segment, you can do it in any order you like. I'm going to do -6, -2, because I just feel like it, which gets us -8 squared. And then we're going to add on to that. I'm going to do 1 minus -2, because why not, which gives us 3 squared. And that equals the diameter of our circle. Now, -8 squared is 64, and 3 squared is 9. 64 plus 9 is 73, so that's root 73, and that is the distance, but we're not done, because the radius is root 73 over 2, because you have to half it to get the radius. So now we have the radius of the circle. Absolutely fantastic. And now we can set up the equation of the circle. So, if you recall, to set up the equation of the circle, we open the bracket for the x-coordinate, and we take the negative of the x-coordinate of the center of the circle. Or if you don't remember why this is the case, just watch my video on deriving the equation of a circle. I like it, it's a good one. Anyway, so you take the negative of the x-coordinate, which is +2, and you chuck it in the bracket. And then you do the same thing with the y-coordinate, so you get y plus 1/2 squared. And we need to set that equal to the radius squared. So we need to square this thing right here. So, remembering how laws of indices work, we can just distribute the squared to the numerator and the denominator individually, and we'll get the root 73 squared, by definition, is 73, obviously, and the denominator squared is 4. And so we're going to set that equal to the radius squared, which happens to be 73 over 4. Really, really horrible equation of a circle, but an equation of a circle nonetheless. Okay, on to the next problem. Okay, so this second problem is a little bit harder, but not too bad. It goes like this. Find the possible values of k such that the point 2, 2 and 2, k have a distance between them of less than 5. Okay, so this is a good problem solving strategy. Just sit down and digest everything that's going on in this problem. Okay, so we've got a fixed point 2, 2, which won't change, so it's just sitting nice and pretty in the xy plane. And we've got another point 2, k, and we know that k can vary because we need to find different values of k, and it's also a letter. So, let's think about what happens if we vary k. If we vary k, because k is in the y-coordinate of this point, varying k will just move this point up and down. So, what it physically means, the distance between 2, 2 and 2, k, is, well, the distance between our fixed point 2, 2, and distance between a variable point as we vary the value of k. And we need to find the different values of k we're allowed to have, such that the distance between the fixed point and the variable point is strictly less than 5. Notice how it doesn't say less than or equal to, just less than, so it can't be exactly 5. Okay, so to do this, we can set up an expression using the distance formula between these 2 points, set it less than 5, and then solve. So let's do that. And by the way, I'm not going to do the distance formula like exactly. I'm going to square both sides first. So I'm going to have the square root of blah, blah, blah less than 5, and then I'm going to square it first. Just skip a step, easier, right? So first bit, we're going to open our bracket and find the difference between the x-coordinates, which in this case is just 0, which is cool. Sorry for yelling down the mic just then. I apologize. Anyway, right? So, and the difference between the y-coordinates is k minus 2 squared, and that's less than 25. So just do the normal distance formula and square both sides. You'll get to this point. You know what I'm talking about, right? Anyway, so now we can do a bit of simplification. 0 squared, that's 0. K minus 2 squared, we can expand that. And then less than 25, it's less than 25. Right, so k squared minus 4k plus 4 less than 25. And then we can subtract 25 from both sides, and we get that k squared minus 4k minus 21 is less than or equal to 0. Now, we're faced with a quadratic inequality. If you recall, I've done a video on quadratic inequalities, or you already may know how to do them. All you need to do is solve this for the roots of this specific polynomial here, so when it equals 0, and then you can draw a little graph to find the exact values of k where this is all allowed, where this polynomial outputs values that are less than 0. Right, so we need to solve this. If you can do a nice bit of factoring here, and you can get that the values of k, the roots of this polynomial are k equals 7 and k equals negative 7 and positive 3. K equals minus 7 and positive 3. And then, you can draw a graph of this polynomial, which intercepts the x-axis at negative 7 and 3. Horrible quadratic graph, but yeah. By the way, if you don't remember how to do this, yeah, watch another video, or you might be able to understand what I'm doing from here. So we've got this polynomial for k, and we know that it's less than 0. And to find the values of k, where this polynomial outputs less than 0 values, we can draw the graph and then look at this bit here, where it's clearly outputting negative values. And we can see that clearly the values of k are k less than 3 or greater than 7. So we can write down our final answer as the possible values of k are k less than 3 but greater than negative 7. And now, boom, that seems pretty cool, right? Anyway, my boys, thank you for watching this episode. It's probably not been a short one, to be fair. Doesn't feel like a short one recording it, but yeah, I hope you've had a wonderful time watching this video, and I hope you've learned something, and I hope you now see where the distance formula comes from if you didn't before. Anyway, thank you very much for watching this episode of Maths with Hamblin, and I'll see you in the next one. Bye-bye!